This video is on mass spectrometry. So at AS we look at mass spectrometry of elements and trying to work out the relative atomic mass of elements from their mass spectra. In A2, in Chem 4, we look at the mass spectra of molecules. When electrons are fired at molecules, they will fragment, the bonds will break, and they'll fragment into different pieces. So we have to understand, firstly, how molecular ions fragment, and then secondly, I'd be able to identify the peaks of a mass spectrum in terms of fragmentation, so be able to work out basically what a molecule would fragment into. So I want you to consider the following molecule that I'm going to draw. It's a ketone. And I want you to imagine that an electron gun has been fired at this molecule and that the molecular ion has been formed. So this now has a positive charge. Now what will happen to this molecule is it will break down into two things. One that is positively charged and a free radical, because basically what this molecule is, it is a free radical as well. It is a positively charged free radical. Because it's lost an electron, therefore it will have an unpaired electron as well. That's what a free radical is. So when we draw the molecular ion, when it's lost an electron, we'll make it positively charged, but we'll also indicate that it's a free radical as well by drawing a dot. And what that will break down into, in some occasions, is it will break down into something that is more stable positively charged and another free radical. The two things that are stable when they're positively charged, or rather more stable when they're positively charged, is firstly an acylium ion, which would be this bit here, or indeed the other side as well. You could have this bit as well. So if the red section turned into an ion, what you get is CH3, C, double bond O plus. And this carbon that's positively charged here is more stable because it's electron deficient anyway, because you've got the oxygen pulling electrons away up to the oxygen. The green segment would be C double bond O and then CH2, CH2, CH3 plus, with the positive charge being on the carbon of the carbonyl group again. So that is called an acylium ion, and that is fairly stable as far as carbocations go. The other thing that would be fairly stable is an alkyl group. So for example, just this CH2, CH3 here. So again, that's a carbocation with the positive charge being on CH2, the C of the CH2. Again, this carbon, if you think back to last year at AS, you know that carbocations are more stable with more alkyl groups around it. If this carbon has another methyl attached to it, that would be even more stable. And if it had two methyl groups attached to it, rather three methyl groups attached to it, sorry, it would be even more stable. So if it's a tertiary carbocation, it's more stable than a secondary, more stable than a primary, just like last year. To draw an equation for this, let me just delete some of this stuff. In fact, I'll delete the whole lot. So to draw an equation for this, what you'd start off with is your molecular ion, just like this, and what you'd make on the other side of the arrow is one of your ions that is stable. So I'll do the CH3 C double bond O ion, plus the rest, so that's this bit that's come off, plus the rest as a free radical. So you've got a positively charged ion, and you'll have CH2, CH2, CH3 dot as well as a free radical. So your ion has come from this side, and your free radical has come from this side here. That won't be the only fragmentation you'll get a large range of different fragments being detected. Now, it's worth noting here that this fragment here will not be detected in the mass spectrum, in this case, for this fragmentation, because it's not charged. Remember, for something to get detected in the mass spectrum, it has to be charged, because otherwise it won't be accelerated, it won't be deflected, and it won't be detected. This is the only part of this that will be detected. So what you'll get is a peak that corresponds to the MR, the relative mass of this fragment. So that'll be 12 plus 16, which is 28, plus 12, which is 40, plus 3. So you'll get a peak at 43, which will correspond to this fragment here, as well as the peak that will correspond to this whole molecule, which would be the peak furthest to the right of the mass spectrum. So using that information, we should now be able to identify peaks of a mass spectrum in terms of the fragments. So I've got an example question here, and basically what you're looking for is what the acylium or alkyl groups would be if the compounds you have would fragment. So these three questions here are all to do with these two isomers up here. They're both isomers of each other, you just got the double bond that's moved along a carbon. So the first question says, identify the isomer as a major peak at an MZ value of 57 in its mass spectrum. So it's going to be a fragment, and the first thing I would check is the acylium ions, because they are more stable than the alkyl ions that would be created. So the acylium ions that could be created from Q are either Cedal bond O CH3 or Cedal bond O CH2 CH2 CH3. So it's worth just adding those up and seeing what those would add up to. So if we had this bit, that would have an MR of 12 plus 16 plus 15, which would be 43. If this was the fragment here, the MR would be 12 plus 16 plus 15 for the methyl group, plus 14 plus 14 for the two CH2 groups. So that gives you an MR of 71. And then in the R isomer, you've got two fragments that would be the same, the Cedal bond O CH2 CH3. Because it's symmetrical, you also have the same on this side, and that would have an MR of 57. So that is what your major peak is. So you have to identify the isomer as a major peak 57. The isomer is R, and you might want to just put in what the fragment is, so CH3, CH2, Cedal bond O plus. Then it says, write an equation for the fragmentation of the molecular ion of this isomer to form the species that produced the peak MZ equals 57. So that is write an equation like we were doing in the previous slide. So first thing you start off with is the molecular ion. So you have CH3, CH2, Cedal bond O, CH2, CH3, and that's going to be positively charged, and it's also going to be a free radical, and that's going to make a positively charged group, which is which has this purple box around it, that bit, that acylium ion. So that's CH3, CH2, Cedal bond O plus. And then remember a free radical of the rest of it, so the CH2, CH3 is also going to be made, but it won't be detected because it's going to be a free radical, it's not going to be charged. So CH2, CH3, and then that's going to be a free radical, so make sure you put the dot on the appropriate carbon, which is the CH2 carbon. The next question says, predict the MZ value of a major peak in the mass spectrum of the other isomer. Now notice it says a major peak, not the major peak. So there's a number of different values you could put, and I would suggest either 71 or 43 from your working from before. So either one, you could have 43 or 71. So I've put that in. Just write that out again for you so you can actually read it. There you are. And those correspond to the two acylium ions that Q would create. So I'm just going to show you a couple of other example of past paper questions just to show you that they don't get much more difficult than that, to be honest. So here it asks you It talks about this molecule here, which it refers to as DEP. It says include major peaks at 222, and that's the molecular ion, that's that whole thing, and at 177. And it says write an equation of the fragmentation of the molecular ion to form the fragment that causes the peak at 177. So the first thing you've got to do is work out what the fragment is. And what I would do here is work out not what the large fragment is, the 177, but what the other bit is. So if you do 222 minus 177, that equals 45. And now what you've got to do is work out which bit of this molecule which would come off would weigh 45. That's not going to be this bit that's big. It's not going to be the bit that gets detected, but it's going to be the free radical bit, if you like. So what I would do is work backwards from this bit here. So a methyl group weighs 15, so that's not 45. Add a CH2 group, so that's 15 plus 14, that's 29, that's not 45. Add the oxygen as well, add 16 to the 29, and that does equal 45. So this 45 corresponds to this bit of the molecule here. And so what you'll get left with is just this C double bond O, which is an acylium ion essentially. So to write the equation, notice they give you a lot of space, so you can put the benzene ring in. You put the benzene ring, and then, so you're just drawing the molecular ion here. And on the bottom. Remember, the molecular ion is positively charged, but also a free radical. And that goes to produce the acylium ion. Remember, only one of the CH2, CH3 groups has come off, so I'm just going to put it on this top one. And then plus the OCH2, CH3 bit, so OCH2, CH3, and the free radical bit is going to be on the atom that was joined to the C, so that's the O, so we'll put the free radical dot there. So there's the equation you should be writing for that. And then a final question here, just I want to show you that the different peaks can arise from a different reason, and that is the idea that atoms in the molecule can exist as two isotopes, and if the two isotopes are almost equally as abundant, you're going to get molecular ion peaks that correspond to both those isotopes. And you can have a number of different molecular ion peaks depending on how many of these isotopes could exist in the molecule. So here we've got a molecule that has 4 chlorines in. The molecules are either going to have bromine or chlorine if they ask you a question like this, because chlorine has 75 to 25% ratio of the isotope, sorry, and bromine has about a 50-50 ratio of the two isotopes. So here it asks you to work out how many molecular ion peaks you get from this molecule, and to do that you've got to work out how many different combinations you could have of the 4 chlorines. So you could have 4, just make the pen a little bit smaller, you could have 4 35s. So you could have all 4 chlorines being the 35 isotope. You could have 3 35s and 1 37. You could have 2 35s and 2 37s. You could have 1 35 and 3 37s, and you could have all 4 being 37. So that is 1, 2, 3, 4, 5 different peaks there. So you could get 5 different molecular ion peaks because of the different combinations of chlorine isotopes you get in the molecule. The most likely one is going to be the one that has all 4 being chlorine 35, because that is the most likely one that could be, that's the most abundant one. So the most likely one is going to be all 4 of that. So to work out the most abundant molecular ion peak, you're going to work out what the MR is of the whole thing, but take into account that the 4 chlorines are going to be chlorine 35. So that's going to equal 4 times 35 for the chlorines, plus 2 times 16 for the oxygens, plus 4 times 1 for the hydrogens, plus 12 times 12 for the carbons, and that equals 220, I believe. hopefully that's covered most of the questions you'll have seen, or all the questions you'll have seen in past paper questions you've been doing. If you've got any problems, then please come and find me in revision sessions or in class.